itself. So this entire flooring structure here, all of this and all the detector hardware is all suspended from above, right? So this here is then also above water. So any space that isn't that's in the cavern that isn't the acrylic vessel itself is filled with ultra pure water. So inside our acrylic vessel, like where we're actually like detecting neutrinos and other particles, that's filled with our liquid scintillator, our linear alpha benzene. Being a liquid scintillator, it produces light when you have ionized particles interact with it. So as you have ionized particles going through, you get flashes of light. Back in the SNO days, this was filled with heavy water, and that produced light by a process called chromatography. So when you have an ionized particle that can travel faster in that medium than light can, you basically get like a cone of light that is produced by that charged particle as it's traveling through, and you end up with these like nice ring patterns on our PMGs. So the structure around the acrylic vessel that holds our 9,000 whatever photomultiplier tubes, and because it's also a sphere kind of looking around, when you had this Cherenkov radiation kind of go through and it was producing like this cone of light, you know, showering in the direction of the particle going through, you would end up with like a ring sort of being that. And if you assume that it's a cone, you can take like that circle pattern, depending on how wide or how narrow it is, and then extrapolate that cone out based on, you know, the speed of your expected particle and figure out a point of interaction. But then your center of that cone is also like another point, so you can have good directionality with your particle in that sense. So you have your interaction point from the tip of the cone, center of the base of the cone, draw a line through it, and you can go through there. So SNO, really looking at solar neutrinos, that was incredibly important to be able to do, because any solar neutrino, to be able to confirm that yes, it is a solar neutrino, it's got to come from the sun. If it doesn't come from the sun, it's not a solar neutrino. So basically, you look at the base of the cone, you look at that point, draw a line. If it doesn't point to the sun, it's not a solar neutrino. So that was the basic reason why we use heavy water and why you use Cherenkov radiation to detect neutrinos. For scintillation, the ionized particle is coming through and it interacts with the scintillator, you get basically an isotropic amount of light. So almost like a circular bomb almost, right? Sorry? Yeah, the stuff that we have on the inside now. So, oh, no, that's just a photo of what the inside of this like looks like. We use blue LEDs to kind of illuminate it, so it's not a blue liquid, it's a clear liquid actually. But anyway, so because we get much more light out of the scintillation than we do the Cherenkov radiation, but the drawback is because it's an isotropic amount of light, we have good position reconstruction. We can look at all the event and all like where the light hits and say, yep, the event happened there inside our detector. We just don't know what direction it came from. So that's the trade-off, right? We get much more light when particles come in and interact with the scintillator, but we just don't necessarily know where it comes from. There's tricks. We can kind of sort of do things, but not. Okay, I'm going to highlight here. Concrete, steel. So then this is now standing over water. As you can see, the depth is actually fairly large. It's in the center here is our deck clean room. We're not going to go in here. This is where we do very, very cleaner science and things. Yeah. But at least in this sense here, we can kind of get an idea of, you know, the top of the cavern here. We can see, you know, similar to the rest of the old side of the lab, there's the like sprayed on shotcrete that's kind of painted over. It's not smooth like the new lab. So that was just like the way that they did it. And like when they first built this location, they didn't do the hand travel finish. So you can see we still have all that along here. But then you'll see, you know, this whole bunch of steel that's then like mounted into the side of the walls and sort of like gone down to the floor. And that's because everything here is suspended from the top. It's not a floor, it's being suspended. So, yeah, don't mind the boats. So, we have, you know, these 9,000 photomultiplier tubes. We need to be able to, well, one, turn them on, and then read information from them. So photomultiplier tubes.
They collect information?
They collect photons. So they are single photon detectors. So this is actually what one of the tubes looks like. This space here would be what's looking at the PMT, and if this were to be on and live, that would break it. So these need, you know, pretty much darkness for these to work properly. They're incredibly sensitive. We put them in a structure that has a very simple, like, reflection color to them, so then if a light kind of comes off to the side, it gives it a higher chance of actually hitting the PMT. It increases our coverage. This is is only 8 inches in diameter. So each of these will have a place where a cable connects, just on the back
That's
over here.
the big cable?
These are the big cables.
Look behind you.
I'll point to these in a second. So all those cables run to the back of the PMTs there. They're actually O-ring sealed on the outside and the inside to prevent water from coming in, because all of this is working underwater. So the way that the PMTs work is that they have a photocathode on the front and then an electrical anode at the back. And you hold this at a fairly large like high voltage potential. So nominally, like these should have, you know, a 2000 volt potential across them. So your cathode will be at 0, the anode at 200, or vice versa, whatever. But the way that these need to work is that there are additional what we call dynode stages. So there's a bunch of other plates inside of it that are all held to little different potentials. And so when you have a photon come in and it hits the photocathode, we then, or these utilize a process called the photoelectric effect, where a photon will deposit onto the photocathode and it release a photoelectron, right? And the energy of that photoelectron is proportional to the energy of the photon coming in. So you can kind of get an idea of charge just looking at that electron. But one electron is never good enough to look at a signal, so we need to amplify it. So this is where the photomultiplier, like multiplier part, comes from it. So each of these dynodes held at different potential essentially attract that electron to it. So you get one electron, it hits the first stage dynode, that knocks out 2 electrons.
Okay.
Then those 2 electrons go to the next one, and it's exponential. So eventually you end up, you know, if you have like 10 or whatever dynodes, you end up with 2 to the whatever. So you will end up with this huge charge avalanche hitting your anode, and that produces a charge pulse. But all of that, like that pulse signal, is also proportional to the incident photon. So if you have a higher energy photon, you get a larger peak, and so you can kind of do some analysis to it. We don't really. We more work with coincidence, right? So we're basically looking at the total amount of PMTs that saw light and collecting that all together to get an idea of the energy of the event itself. We don't necessarily care individually what this sees. It helps, but we kind of just want to know, did you have a whole bunch? How many did you do? And then the relative timing. So, now I'll point to cables, and let's go this way so less of a mess. So each PMT has a cable. So we have 11 of these hardware racks here. They can have 2 of our crates. Each one of these crates is subdivided into 16 sections. Each one of these section cards can provide the high voltage for 32 PMTs. So and also we have the single for 32 PMTs. This is then subdivided into 4. So you can see we have 8 cables, 8 cables, 8 cables, 8 cables, so 32 all the way here.
16.
Yeah, and then times 16, so 512 potentially up to this. So you can see, like, you know, if we have 19 of these crates, you really get up to a large amount of numbers there. Each one of these cables is then fed out into the back here, into this whole entanglement of mess, and eventually gone through and then put through deck there. So each one of these like openings for the cables where it's like fed through is then resealed to not let gas through or let light in. So all of this needs to be light tight. Like we need to be able.
Dark.
Yeah, exactly. There's a whole bunch of like darkening stuff here to help, like, well, one to help like gather and bundle things, but then every opening where the cable like feeds through is then sealed up to be dark.
And Peter thinks he has problems wiring things up, eh?
But these look messy.
Labeled. Well,
They're very nice. They're very clean. I'll give it that.
They're decent, and I mean, like, they're kind of okay to work on. So, I mean, all of this is off, so I can do this. Thank you. So fine. That. So these crates are divided into 2 sections. There's this side here that supplies the high voltage, but then it also like will see the charge current pulses from the PMT channels and separate those out, because those charge pulses are also at that like 2000 volt baseline, and computers can't handle 2000 volts. Even if it's like low current, no, you can't do that. You need to bring that back into like some kind of like low voltage logic state. So again, this was designed with some serviceability in mind, which is good, because PMTs go bad. and you gotta deal with them. Yeah. It's also designed to like spread out. So a lot of like passive circuitry that sort of happens here, but you see like where the cables kind of terminate, they just kind of go to the end onto these panels here. This whole crate shares just one supply, so one high voltage supply. Each PMT is very, very, very low current draw, so you can like power up to 500 PMTs per one of our supplies, which is great. That all branches out into parallel into all of these, and then you have the high voltage come in through this connector here. It's then branched out into the 4 through these relays. Past the relays, each one of these will have a small surface mount resistor here to sort of branch that up and feed through. So this one would be the relay for these guys. That one would be the resistor to then feed these guys. This one here goes there, that one there goes there. So once it's past this resistor, it branches out again into a parallel group of 8 to then feed each one of the PMTs. Every PMT was tested way back in the day to sort of figure out what its nominal voltage is. Every PMT is its own unique device, right? They'll kind of have, you know, more or less gain depending on what you send a voltage to, so you can kind of tweak it a little bit. Each one of these resistor values is set to basically tune it to where it's happiest within a certain region. When our tubes go bad, and they do, we, like when we're running, we kind of lose 3 to 4 PMTs a month.
A month?
And when they do, instead of sending a signal back, they'll send down what we call breakdown pulses. And so this is a whole bunch of charge that essentially like goes back up the stream and can potentially damage these feed resistors. And it does it in a sort of way. So if you have a PMT go bad, it'll end up damaging one of these resistors here and let it go. If there's still charge to then dissipate, if the breakdown still needs to continue, the next thing it's going to hit would be the resistor that feeds the group of 8. So if that happens, and suddenly this resistor is no more, when we're running, it'll look like, oh, we just lost all of these, right? If we haven't dissipated that breakdown current enough, the next thing it's going to go through is there's one resistor right there, this R252. It will then take that one out, and if that's the case, it then looks like we've lost all of this. So that's fine. We just tell our control software, okay, we're going to ramp this down, we'll open up these relays, we'll make a note of it, we'll fix it when we can, kind of thing. It happens. So when you look at then pulling out, you'll be like, oh, yeah, okay, that resistor went bad, so that PMT is bad. We pulled that, replace the feed, all good. Keep going. But,
So how often do we check it?
We tend to do, like when we're running, we do maintenance, you know, every few weeks, unless some really bad stuff happens, then we gotta fix it, you know, sooner.
Okay.
But, you know, kind of just.
Is there any magnet kind of thing?
No, so there's a set of rails,
Okay.
top and bottom here. Sorry.
Yep.
Most of what I do and work on is this stuff, so I can kind of do this blind.
It's pretty good. I'm watching you go. The serviceability is actually pretty damn sweet. Yeah.
Yeah, it's you know, I should have pulled it up. So on the back of these, like what's holding the cables in place are like these metal brackets to ensure that like the cables can't go anywhere once this is secured in place. And then the back side of it has these sort of like self-locking standoffs. So and they're plastic. So to be able to like get these what we call pallet carts, to get these off so you could actually like service this board elsewhere, you need to like remove the bracket and then take a pair of pliers to like depress the lock for these standoffs and push them through. So they're a little bit tedious to be able to like undo. So we do a lot of work right here. Like I have a battery operated soldering iron that we'll just bring out here, slap on the top of the rack, and then do the work that we need to do if we do need to solder on these. So serviceability, yeah. Transportability, no, not really. Depends, because the other thing too, right, is that we basically have a understood map at the moment of where each PMT is connected to which board. right? So we have a map and nomenclature to say, okay, this is crate 14. This would be slot 4, and then if you go up 4 PMTs, that would then be channel 4, right? So that number would tell you which PMT it is, and then that database would then match it to the name of the PMT down the line, and then where that is in the detector itself. So if I were to remove these pallet cards and not put them in the right direction, the right orientation, we'd be messing something up at the data level, right? And you could document that and potentially make changes to update, but if we are going to do that, we're going to install things exactly as they are, because that will completely mess up the way that we expect the data to look. So if I were to be pulling all these out, that's why we just write Sharpie marks on each of these so we know which way they're supposed to go. And I'll write down markings if I do need to replace these. On the computational level, it's not that much of an issue. Because these boards are essentially interchangeable. So these would be the computational sides of the boards. And we've been trying to keep these working since 1997.
Oh.
So these were the ones originally designed for SNO. They still work really well for SNO Plus data taking. They potentially work even better for SNO Plus data taking. They're basically the limitation on SNO was the total amount of data that you can write out had to go to tape drive storage. Not big wheel tape things, but digital tape drives. They would hold a few gigabytes each, but they had a very comparably slow write speed. You can only basically do 1 megabit per second, total write to the tape drives. So you would throttle the detector essentially to then ensure that you had capability to write out all your data, including some burst capabilities. Now we just have everything connected on through an Ethernet cable to a server, and all the data just feeds to a server, which can then write to hard drives, and then we can use the internet to then transfer it off-site. So in the time, in the time between SNO ended and SNO Plus started, servers got to the point where they could keep up with us, right, and not necessarily be too bad. So we're able to really crank the speed on all these electronics, which is a lot of digital components, but in terms of things, there's only 3 FPGA chips on here, which for 1997 would have been mighty expensive, but everything else more or less is off the shelf. There are some custom chips here, so you can see here these SNO Ints, the ones that are listed as UPenn. These are custom integrators. They basically do charge integration on the PMT pulses going through. So I mentioned how you can kind of get an idea of the energy of the PMT by looking at the charge. Well, if you integrate over those pulses, you can kind of get an idea. So we do that. Just doesn't give us the most information. We'll head out soon. On the back side of these are discriminators that actually sets the thresholds per PMT level. Those are also custom chips. And then these guys here, I don't know if you know your Northern Ontario history, but Canadian Electronics Company history, but these are Nortel chips, so Northern Telecom. So they went defunct, mid 2000s ish.
I've spent my entire IT career dealing with every place I go called the Wall of Nortel Networks.
Right.
We have one up in the mezzanine.
Anyway, so there's one of these chips per PMT channel. So these are our most abundant custom chips. There are 10,000 of these through here. We can't get these anymore, but they do a lot of the computational stuff for the PMT channels, and it's something special to see the Nortel logo and then SNO underneath it.
Yeah, it is special. Yeah.
But then otherwise, it is a basic not single function, but very hyper focused computer. You have some computational stuff. There's a bunch of analog to digital converters, digital to analog converters. These get 5 power voltages to them, so a plus and minus 24, a plus 8, and then plus and minus 5. So VCC is plus 5, VEE is minus 5. To then give other sort of computational voltages into places. There's a bunch of voltage regulators here, which some of them produce a fair amount of heat. So then there's heat sinks on these guys. There's a whole bunch of stuff. Memory. So in the process, when we have a PMT hit come through, we will record very basic information on it. So like a few charge integrations, a relative timing measurement, and then basically like where, like for this pulse, what PMT hit it. So the basic information that we need to be able to identify the PMT. That then gets saved into memory, right? So this is RAM. This is 4 megabytes of RAM.
4?
Across the entire detector, that means there is 1.2 gigabytes of memory across the entire thing. And for 1997, 1.2 gigabytes of memory would have been a lot for a computer system. But right now, that's 4 megabytes of memory. That is able to hold 1 million and a bit like PMT pulses, because the amount of data like in that PMT
That's
pulse
so
is
small.
only 96 bytes.
Oh, okay.
So again, it is entirely possible to overload this because we just use it as a first in, first out array. So you write a like pulse in, and then it just like queues up. But the magic of the system is that we don't need to write out the information for every single PMT pulse. PMTs are relatively noisy instruments, and you know they'll just produce noise pulses on their own. But it's only when we have enough PMTs that fire all together at the same time to essentially say, yes, this is an event, that we then tell the detector, okay, if you had a PMT pulse that happened at this time, send me that information. Otherwise, that information is on memory and then goes away. So we noise filter just to see the things that we want to see, to get that information all together. And when we do that, like when there's an event, we basically like say for the detector, okay, any hits from this point on to like the next 400 nanoseconds are valid, put it inside this window, and give me that information. After that, we reset, we wait for the next thing, and we're able to go to it. So we're able to record an event every 420 or so nanoseconds, which is pretty damn fast. That basically gets to the point of like, well, we can sustain 20 kilohertz of an event rate. It will start to freak out a little bit, but we can do it. We like to run at around 2 kilohertz of event rate. That gives us enough information to be able to, you know, get down to like a really low energy threshold. But that 400 nanosecond window is important because it takes light about 100 or so nanoseconds to like go from one PMT to the other one at the opposite end. So that's about how long that travels. So if you imagine an event happening inside the middle of the detector, you'll get light on one side, right? If it's dead center in the middle, you'll get light over here and over here around 50 nanoseconds away from that point, right? Then, if you have anything bouncing off, right, then it has to go from here to this side here, you add another 100 nanoseconds. So within that event, you might get those first reflections. Now, if you had light that goes through here, but then it bounced off of the AV, that's acrylic, so you might get some total internal reflection that happens. You bounce that way and you go here, that's going to come in at a different time. So whenever you have light going through, just due to the optics of everything, you'll have direct light, you'll have indirect light, you'll have reflections, you'll have second reflections, you'll have a whole bunch of other things here. And because we have that resolution within that window, and our instruments are able to sort of like tell the difference, you know, within a nanosecond or so, like different PMTs being hit, we can see these different light paths and things.
So, using these data,
Yeah.
like whatever records we have, can we predict like when will be the next one?
When the next like supernova, or
No, like
oh, like when the next thing happens. I mean, so right now, be mindful of the time. So right now, when we're running, we're just our scintillator, like the full cocktail of things. So we're looking at like the backgrounds of the experiments. So we can understand, you know, how much radioactivity we have intrinsic to the material that we're using. We're looking at neutrinos from the sun. We're looking at neutrinos from nearby reactors. So a whole bunch of different sources. And then we also calibrated. So we deployed our own known radioactive sources on the inside to see like what these particles look like inside the detector, to essentially give us a measurement. It's like a ruler on the data, right? So we can look at this data and say, yes, that's 2.2 millielectron volts. So we needed that to basically be able to then like properly look at our data. What we eventually want to do is a neutrinoless double beta decay search. So to do this, we need an isotope that is known to double beta decay, and that's in our case tellurium. So if you walk by the telluric acid plant, that's out that way, you know, the plant that's made of plastic, that is to purify telluric acid to a point where we can take out the tellurium from it, bind it to another chemical, so then we can add it into our detector. If we have a whole bunch of natural tellurium on the inside. There's an isotope of tellurium 130. It's about 30-ish percent naturally abundant, and it will decay. But it is more energetically favorable for it to do a double beta decay instead of doing a single beta decay to get to a regular state. So we want to add a whole bunch of tellurium to our detector to look at an isotope that is going to do this double beta decay. And when you have a double beta decay, you have, similar to a beta decay, you'll have a proton that decays into a neutron, but then you'll have an electron that comes out as well. And then at that same time, you also have an electron neutrino. Or anti-neutrino, can't remember which one. Either way, so you have a neutrino that's coming out and that interaction. With the double beta decay, you get the exact same thing except times 2, right? So you get 2 protons decay into 2 neutrons, those electrons, and then those neutrinos. Now, this is an instance in a decay where you have 2 neutrinos that are the exact same flavor happening at the exact same time. Now, we assume that neutrinos are like every other particle where they have discrete antiparticles, and antiparticles, when in the presence of their matching particle, annihilate, right? We don't know this for sure about neutrinos. It could be that they actually do or can act as their own antiparticle, but since neutrinos just barely interact with anything, but they're so abundant, we don't really get these situations where you just have like one designated neutrino and then another designated neutrino, and will they annihilate and interact? We can't do that. We don't have the control over that, except really for this decay mode, where you have a double beta that happens. You should be producing 2 neutrinos, but if they annihilate or it would interact, they don't happen.
Yeah.
So then we'd have this double beta decay that happens without the neutrinos, which it shouldn't do. But if it does, the energy that those neutrinos would have taken has to go somewhere. They'll be taken by the neutron and they'll be taken by the electron. So what we want to see is those electrons traveling into our detector and depositing the energy, and then see the energy of that in our scintillator. And if we can see that, and if it's slightly higher than we expect, relative to a natural double beta decay, we can say, oh wow, that double beta had no neutrinos inside of it. That would be absolutely new physics, right? That is outside the standard model. That is, not to toot our own horn, but that would be Nobel Prize-worthy physics. That is saying, like, we found something that does not fit the standard model of physics. We found a new weird property of the neutrino that opens up a whole bunch of other things. So the trick right now is to build a detector that is clean enough so you can see these signals, and then loading it with thorium in such a way that you can actually see the phase from that thorium. So we're building up to it.
That was excellent, Matt. Thank you so much.